So no more questions on homework, ready to finish off chapter 9, chapter material. Let's see, where did we get to?
It's 9-7.
9-7 was the last one that we just proved, right?
No. Well,
Yeah, 9-7 is the one that we just finished proving. Let's remind ourselves what we've been talking about. So far, what has this chapter pretty much been about? Similar triangles. So let's remind ourselves of what exactly the definition of similar triangles is. If I know that triangle ABC is similar to triangle DEF, what exactly does that mean?
All their angles are congruent.
So that gives us that angle A is congruent to
Angle B.
angle
Or angle D.
D. Maybe right, and let's see,
Angle B is congruent to angle F.
angle B is congruent to
Angle E.
angle E, and
Angle C is congruent to
angle C is congruent to angle F, and what else?
The ratio of the sides.
Right, so AB, what do I have to write AB over?
D.
DE, so AB over DE is equal to AC over what?
DF.
AC over DF is equal to BC over what?
EF.
And there's exactly what it means for two triangles to be similar. They have all those relationships in common. Now, Theorem 9.7. So, Theorem 9.7, what did that give us?
If the angles of one triangle are congruent respectively to the angles of another triangle, then the triangles are similar.
Yeah, so we'll just call that angle, angle, angle. So if I have two triangles, whatever they look like, if I know that this angle is congruent to that angle, this angle is congruent to that angle, and this angle is congruent to this angle, then I know that the three triangles are similar to each other.
Or the two triangles, yeah.
What did I say?
3.
The two triangles are all similar to each other. Now, actually, we don't need to know that they have three angles in common. We only need to know that they have two angles in common. If I know that these two triangles have this angle the same as this angle, and this angle the same as this angle,
You can prove that the other two angles are the same because all angles of a triangle add up to.
right, the angle sum of these three triangles has to be a straight angle. The angle sum of these three triangles has to be a straight angle. And so if that and that are congruent to each other, their angle sum is congruent to each other. And so you can think about this is the supplement of the sum of those two.
Right. We know by theorem 6.2 that supplements are congruent.
Well, sounds like he knows the exact theorem number.
Of course he does.
But yeah, we know that the sum of congruent angles is congruent. The way we remembered that is the mnemonic device was equals add to equals or equals with the angles. And then we knew that the supplements of congruent angles are congruent. So we actually don't need to know all three angles are congruent. Just knowing two angles is congruent is enough.
So we write angle, angle.
Whatever you want. I do angle, angle, angle. But fine either way. So now we're going to be looking at some other similarity theorems for triangles. It's kind of like the congruency theorems that we had. For congruency theorems, you know we had side, 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 side angle, side angle, side angle.
Yeah.
We're going to come up with similar congruency theorems now. We're going to come up with similar similarity theorems for triangles now. And what information do you need to know that two triangles are similar? Turns out, knowing that two of the angles are congruent is enough. Now we'll look at some other information you could have been given to still conclude that triangles are similar. So let's look at the first one, Theorem 9.8. So we'll scribble that right here.
Want me to read it to you? How you want?
Theorem 9.8. A line that divides two sides of the triangle proportionally is parallel to the third side. All right, so we're going to prove that if, right, the second part of it, so if AD over AB, if AD over AB is equal to AE over AC, make sure I'm not writing any of this wrong, then DE is parallel to BC, right? And I'll scribble out the picture here. It's parallel to BC. So that's what we're trying to prove. Let me scribble our picture. We'll scribble it right here real quick. So the picture that the author gives us is something like this. He calls the top point A. He calls the bottom point B. This point C. So we've got this triangle ABC, and then we add a line to it. And this line is such that it cuts the sides so that this over the total is equal to this over the total. Do not think about those as being exactly the midpoints. They're not necessarily the midpoints. So don't make that mistake. Don't let my picture mislead you. Call that D and E. So I've got this triangle, and I've got the line cutting the triangle. This triangle with the line cutting the triangle. It's cutting it in such a way that the ratio of this to this is equal to the ratio of this to this. I'm trying to prove that this line is parallel to this line. You understand what we're trying to prove? Okay, so how are we going to do this? How am I going to prove that this line is parallel to this line? The way that I'm going to do this is first I'm going to...
Excuse me?
Go ahead.
I know, it messes you up every time. Good morning.
Good morning.
Have we missed anybody?
I don't think so.
Awesome. Okay, that's awesome. Okay, have a good day.
You too.
Okay, thank you.
Okay, first thing we're going to do is we're going to draw some parallel line through D. Move D up a little bit so we can draw a parallel line through it. So here is our parallel line through D. And it's going to intersect segment AC over here at some point F. With me so far? Okay. I'm constructing it so that this line is parallel to this line. My picture's lying.
Okay, yeah, I was like, that doesn't make sense. But okay. Yeah.
We are ultimately going to try and prove that F and E are the same point.
Right.
Therefore, DE is parallel to BC.
Right.
So I construct DF parallel to BC. I need to prove F and E are secretly the same point. And therefore, DE is parallel to BC. You follow me so far what we're out to do? So the whole crux of the point is to show that F and E are the same point. So let's really quick write that. Let L through D such that L is parallel to BC. And let, what do we call the point of intersection? F be the point where L intersects what?
AC.
Intersects AC. Okay, so we got that. What I need to argue is that ADF is similar to ABC. If ADF is similar to ABC, then AD over AB is equal to AF over AC. But I already know that AD over AB is equal to AE over AC.
Therefore, AF.
So I'm going to get that AF is equal to, its length is equal to AE. So the crux of the proof now is to show that this triangle is similar to this triangle. How can I do that? How many angles do I need to show two triangles are congruent? Two.
You have.
How does the top of the big triangle compare to the top of the little triangle?
It's the same angle.
It's the exact same angle. Okay? Now, how does this angle compare to this angle?
They're
They're corresponding.
corresponding.
They're corresponding angles for these two parallel lines. Picture's line. This line is parallel to this line. Here's a transversal cutting them, and so these two are corresponding angles. So, 2. Observe that angle ADF is congruent to angle B. Those are corresponding angles. And angle A is congruent to angle A. Right? So that gives me what?
That the triangles similar.
That the triangles are similar. So triangle ABC is similar to what triangle? ADF. Good. Okay. So then, if I know that these two triangles are similar to each other, that gives me all this information. In particular, it gives me the ratio of the side lengths. So I know that AD, then, well, we'll start with AF, then AF over AC is equal to what?
AD over AB.
AD over AB. Given in my information, AD over AB is equal to AE over AC. You see that? So if this is equal to that is equal to that, then this is equal to that. So maybe just make sure you see that all together. So I know that AF, sorry, that's an A, over AC is equal to AE over AC. Or in other words, I know this times this is equal to that times that. Or if the denominators are the same, then the numerators have to be the same. However you best see it. So then we get that AF length is equal to AE's length. You with me? And if two segments have equal length, then those two segments are congruent. So I know that AF is congruent to AE. How many points are there on this segment, on this side of A, that give us AF? 1. You remember going back to our congruency terms? There's one and only 1 point on each side of a line that gives you a segment congruent to a given segment.
Yeah.
So, if AF is congruent to AE, that means that F is equal to E, which is what we were after. So just to make it completely explicit, therefore, what? Ultimately, what were we trying to show?
Parallel to BC.
Then DE is parallel to BC, which is what we were after. Good?
Yeah.
Any questions on that?
I just wouldn't have made the jump to F equals E for some reason. But I think
You're saying right here?
no, at the bottom.
You're saying this to this. That's the only way we can say it. We've done that similar proof type thinking a bunch of times, where most of the time when you're trying to show 2 points are congruent or are the same point, you show that the segments from the same point to that point are congruent. That's your standard way to do it.
Yeah, okay, that makes more sense.
Anything else? All right, so now we'll move on to our next theorem. Let's see, we just did 9-8. So let's see what 9-9 wants from us. Given triangle ABC and A prime, B prime, C prime with an angle and two sides proportional, prove that the two triangles are similar. Okay, so we know that one of the ways we can figure out two triangles are similar is if you tell me that their angles are congruent to each other. This next one we're going to show actually, if you just give me that two of their sides are proportional and the angle between those two sides is congruent, That's enough information to conclude that these triangles must be similar.
Well, you can conclude that they're congruent. So,
No, just similar.
well, can't you? Because it's
No, we'll draw a picture that makes it very clear that our triangles are not congruent. So we'll pick this triangle and then try and draw one that is obviously smaller. I'll try and make so our picture doesn't lie too bad. So we'll call this A, we'll call this B, we'll call this C, we'll call this B prime, A prime, don't know why I went so close to the top, C prime. So there's our triangles. So what theorem are we on?
9.
9. So we're trying to show that if angle A is congruent to angle A prime, so if this angle is congruent to this angle, and the proportionality between this side and this side is the same as between this side and this side, then the triangles are similar. So if we have that, and we have that A prime B prime's length over A B's length is equal to A prime C prime's length over AC's length, then we have triangle ABC is similar to triangle A prime, B prime, C prime, right? That's what we're trying to show. So I know that this length over this length is equal to this length over this length. Or in other words, those two sides are proportional to those two sides. Notice that it's the two sides that we use to construct the angle. Very important. The same way that we kind of had side angle side, this is kind of like the side angle side version for similarity. Yeah, sides proportional, angle, sides proportional. Good? Okay, so what is going to be our big idea with this one? First thing I'm going to do is I am going to construct a triangle congruent to this one at the top of this, and then I'm going to prove that the big triangle is similar to the smaller triangle, therefore it's similar to this. So first thing I'm going to do is I'm going to come over here and I'm going to pick, try and not lie with my picture too much. Is that roughly the same? No? Okay, well, tough. You're going to have to deal with a bad picture. I'm going to come pick the point. Let's see, where are we on? ABC. I'm going to pick D over here and E over here. And I'm going to choose those points so that this length is the same as that length, and this length is the same as that length. That's how I'm going to construct this triangle. And so then this triangle is going to be congruent to this triangle. How do I know that? Side angle side. They have a side the same, an angle the same, and the side the same. And then I'm going to argue that big triangle is similar to small triangle. And therefore similar to that. With me? So let's do that really quick. Let D in segment AB and E in segment AC such that AD is congruent to A prime B prime and AE is congruent to what? What's AE congruent to? A prime C prime. You still awake out there? Alright, number 2. So, what do I know? Let's think about our given information here. I know this, right?
Right.
8.
So what does that give me? I know A prime B prime over AB is equal to A prime C prime over AC.
You could do
Now-
AD over AB is equal to.
Perfect. So she's saying replace the A prime B prime here with the AD.
Right.
So I know then AD, how does AD's length compare to A prime B prime's length? They're the exact same number. So I'm replacing this number with the exact same number. So that over AB is equal to AC, whatever that length is identical to that one's length. AE over AC, right?
Yeah.
So now I know that this line, DE, cuts the triangle, so in a way that the ratio of that side is equal to the ratio of those sides. So then what do I know? I know what?
You know that they're similar.
Well, you're skipping too fast. How do I know they're similar?
DE
is parallel to BC.
Yeah, from this proof, I now know that this line is parallel to that line. And then I'll get the angles and the similarity that I want.
Okay.
So now I know that this side is congruent to this side. So that is equal to that. And so DE is parallel to what?
BC.
BC by 9/8. You with me?
Yep.
Okay, so now I've got that. So 3, now let's argue for our similarity. What do I need for similarity to say that the big triangle is similar to the small triangle?
3
Two
angles.
angles.
Or
3, but just 2 angles. I already have the top angle for both of them. Notice that angle A is the top of both the small and the big triangle.
Yeah.
So I just need one more angle.
Alright.
So what angle should I use?
B here to B.
So ADE is congruent to angle B. How do I know?
Corresponding angles.
So then angle ADE is congruent to angle B, which gives me that triangle ABC is similar to what?
ADE.
ADE. Triangle ADE. Which is congruent to this. So then, I know that angle B is congruent to angle ADE, which is congruent to, what's angle ADE congruent to?
A prime, B prime, C prime.
Yeah, or we'll just call it B prime since there's no confusion there, but yeah, you see it. So angle B is congruent to angle B prime, and angle C, or angle A, is congruent to angle A prime. You see that? And so, triangle ABC is similar to triangle A prime, B prime, C prime. Good? Any questions on that proof? Okay. So now, our next theorem, Theorem 910, is if the sides of one triangle are proportional to the sides of another triangle, then the triangles are similar. Okay, so this time, if all the sides are proportional, then the triangles are similar. So what does that mean? If I've got my 2 triangles here, let's try this time to get a picture that somewhat doesn't lie. And not just do half like we've been doing each time. Although that probably still came out close to half. So I've got these 2 triangles. Once again, we'll call them A prime, B prime, C prime. So here's ABC and A prime, B prime, C prime. This time I know that this length over this length is equal to this length over this length is equal to this length over this length. I'm trying to prove that the triangles are similar. So I'm only given the side information, I'm not given any angle information. You with me? Let's see what we can do here. Keep that scribble. Can't see that very well. Can you see me fine on the camera?
Yeah.
Yes.
You can see that line?
Yes.
Okay. So we'll just put it right here. So this is theorem, where are we on?
9, 10.
910. I'm trying to prove that if A prime B prime's length over AB's length is equal to A prime C prime's length over AC's length. Sorry, that was a length. Is equal to B prime C prime's length over BC's length. Oops, length. Then triangle ABC is similar to triangle A prime, B prime, C prime. So that's what we're trying to prove, right?
So it's like side angle side with similarity.
It's more like side, side, side
Side.
with similarity,
That's
yeah.
what I meant to say.
So one. So let triangle ABC and triangle A prime, B prime, C prime such that their sides are proportional. Right? Or in other words, these three relationships hold. Okay. Let's come to our scribble over here and think about this for a second. How should we make this argument? So I'm going to start by doing something similar to the other one. I may come and mark over on this triangle the point D over here. So I'll mark D so that is congruent to that. And then I'll mark E so that this is congruent to this. Notice this time we do not have that those angles are necessarily the same. So far, for all we know, our picture could look something like this. One triangle could have been like this. My other one could have been like this. And I just came and I marked the points. However long that is, come mark it. However long that is, come mark it. I do not know that that angle is the same as that angle.
Yeah.
Just no side lengths. You with me? Okay, so we'll start by marking out that triangle. And so that will give us this. What information will we have now?
AD is congruent to A prime B prime, and AE is congruent to A prime C prime.
AB is congruent to what?
AD.
Oh, so I know AD will be congruent to that, and AE will be congruent to that. Yep. So what can we then conclude about the triangle over here using these proportionalities?
You can replace A prime B prime with AD in the.
Right, in those. Okay, so replace it.
DE is congruent to
So.
BC, or parallel.
There we go. That's what I was after, seeing if you could see all the way to there. So we can see that this then is going to be parallel to this.
Yeah.
Right?
Which we already knew that because of the. Yeah.
Yeah, so we now know it because this line cuts both these sides of the triangle proportionally. Okay, so now if I know that this is parallel to that, what does that give me?
The angle B and angle AD are congruent.
That which angle is congruent to which?
Angle B and angle AD.
So I know that this angle, then,
B prime.
is congruent to this angle. And I can go ahead and say this angle, well, that's enough because I also know the top is to the top. So I get that the big triangle is similar to the small triangle, but I need to still argue that this one is congruent to this one. So I know big is similar to small,
Right.
but how do I know that makes it similar to this one over here?
Because
So I still am going to have to show that this triangle ADE is congruent to A prime, B prime, C prime. And the way I'm going to have to do that is side, side, side. I wasn't given any information about the angles. So I'll get to this point in our proof, and then we'll finish it off by showing ADE is congruent to A prime, B prime, C prime, and then we'll be done. You with me?
Right. So because it's similar and then they're congruent, they're
Yeah, so
transversal thing.
so far you're wondering how on earth am I going to show those are congruent? We'll get there. First, let's really quick do the argument that big triangle is similar to small triangle. So let D in segment AB and E in segment, which segment?
AC.
AC, such that what?
It's parallel. DE is parallel to AC.
No, we don't. We're going to argue that it's parallel, such that AD is
congruent to A.
congruent to A prime, B prime. So such that AD is congruent to A prime, B prime, And what else?
A is congruent to A prime C prime.
AE is congruent to A prime C prime. That is correct. Oh, prime, prime. Okay, so we've got that. Now, 3. Then I know that DE is parallel to BC. How do I know that? How do I know DE is parallel to BC?
Because of theorem 9.8.
Theorem 9.8. This cuts the sides proportional. Maybe say the since here, just to be a little bit explicit. Since AD over AB is equal to AE over AC. How do I know that that ratio is equal to that ratio? Well, AD is exactly as big as A prime B prime.
Yes.
So AD over AB is the same thing as A prime B prime over AB. And AE over AC is the exact same thing as
BC over.
A prime C prime over AC. So since this is equal to this, I know that's equal to that. So since those ratios are equal, then I know that
By theorem 9.8.
DE is parallel to BC by, what's our theorem there? 9.8.
9.8.
Okay, so just to make it explicit how exactly we knew that those were parallel. It was because of that proportionality.
Right.
Okay, so now, then angle, what's our angle that we cared about? The one we chose, ADE. We could have just as easily used AED.
Right.
Nothing special about always using the left. So then that is congruent to which angle?
B.
Angle B. And, in case you missed it, angle A is congruent to angle A, which gives me that triangle ABC is similar to what?
AE.
Is similar to triangle ABE.
DE.
Thank you. ADE.
Yeah.
Just a test. Making sure you're still awake. Triangle ADE. Okay, so we got that. Now, I still need to argue that this top small triangle is congruent to that triangle. We're going to have to use side, side, side to do it. Right?
Okay.
Now, what is some information I have about B prime, C prime? What do I know about that side length?
It's proportional to the other sides.
Right, so then I know that B prime, C prime's length over what?
BC's length.
Over BC's length. What is this equal to?
The other.
A prime C prime over AC and AD.
Sure, pick one of them. So he said A prime, C prime over AC, right? Now, transfer that to this triangle. What is A prime, C prime in terms of the smaller? What does A prime, C prime correspond to over here?
AD.
So this is equal to AE over
AC.
AC. That stays the same. And that is proportional now finally to, since the top triangle is similar to the bottom, or since the top triangle is similar to the whole triangle, then I know that this side over this side is equal to this side over this side. And it's also equal to this side over this side. Pick one. But either way, we already chose to use AE over AC. But that's the same as DE. And there was the big part that you would have got stuck on if you were doing this by yourself, most likely. Over BC. So you see that? B prime C prime over BC is equal to DE over BC. So what does that give me?
That B prime and C prime is equal to DE, the lengths of DE.
The lengths, perfect. So then that gives me that B prime C prime's length is equal to DE's length. Now if two segments have the same length, what does that mean? they're congruent. So then that gives me that BC, or B prime C prime, is congruent to DE. So now I've got this side is congruent to this side. And so now I know this triangle is congruent to that triangle by side, 6. So then, triangle ADE is congruent to triangle A prime, B prime, C prime by side. Okay, so what? These two are congruent. What does that give me?
Now they're similar to the big triangle.
That the big triangle is similar to that one. Because the big triangle's angles are all the same as this one's angles, and this one's angles are all the same as this one's angles.
Right.
So this one's angles are all the same as this one's angles,
Those are similar.
which is what we were after. So 7, therefore, triangle ABC is similar to triangle A prime, B prime, C prime. Any questions on that?
That makes sense.
So that was theorem 910. Okay, now we got the Pythagorean theorem, and then a cool one about inscribed angles. Well, shove over some whiteboard
Sweet.
rather than erasing. So finally get proved the Pythagorean theorem. I think I've already shown you guys a very pictorial Pythagorean theorem. This time we're going to prove it using a lot of similar triangle information. It's going to be a somewhat cool way to prove it. Alright, let's see if I can get this camera moved. Probably would have been faster to erase the board. Alright. Just make sure I can see that edge. And then just don't use the last foot over here. I think if I don't go past that, I should be fine. Alright, so next we're going to prove the Pythagorean theorem. What is the Pythagorean theorem? I'm going to stop writing out the whole proof and just start being very pictorial. And just make sure you guys follow it, and if you get stuck, we can write out all the logic if you want. So the Pythagorean theorem, you all know the Pythagorean theorem. What is it?
It's the two legs of a right triangle. If you square them, add them together, it's equal to the side of the hypotenuse squared.
Oh, before we prove this, I actually want to talk about a geometric mean. So really quick, I'm trying to draw so that's a right angle up there. So trying to make that look like a right angle. And then drop an altitude down from that right angle to a point right here. What's an altitude?
It's a line.
I create the perpendicular bisector to this line that goes through that point.
It's not a bisector.
And you guys remember that we've already had a lot to say about perpendicular bisectors going through a point.
Is that a bisector?
Not a bisector, thank you. Just a perpendicular line that goes through a point. Not a bisector. Sorry, forget the bisector. So this line is perpendicular to this line, and it goes through that point. So what is this angle right here? Right angle. And obviously a right angle right there. Good? Now notice what happens here. Notice that this angle, let's label some points here. Let's call this A, B, C, that's the point D. I'm going to split the triangle at that altitude, and I'm going to redraw those two triangles side to side here. Hopefully it doesn't look too bad. If I can draw it half decent. So this was meant to be the point A, B, D. Trying to redraw this triangle, and then redraw this triangle. Something like that. This is a point A, D, C. With me so far? Yeah. Okay, so we know that this is a right angle. We know that this is a right angle. And I know that this angle, we'll erase that right there. Yeah, you see it. That angle, look at this big triangle ABC here. Notice that right angle, and that green angle is the same as that green angle.
So they're similar triangles.
So this triangle is similar to this big triangle right there.
Right.
Or in other words, do I have one more color here? Guess we'll just use black. This black angle, this angle, is the same big as that angle because the triangles are similar. At the same time, notice that this angle is the same as that angle.
Yeah.
And this angle is the same as that angle. So this angle, then, has to be
Same as the green.
the same as the green. Because this triangle is also similar to this triangle, because that angle and that angle are the same. So that angle is the same as that piece right there. You see it? So when you take a right triangle and you drop an altitude down to its hypotenuse, you always split the right triangle into two other triangles that are similar to the initial triangle. Yeah, absolutely awesome.
How is that related to Pythagorean theorem?
Well, we'll use this fact to get to the Pythagorean theorem, but first I want to talk a little bit about a geometric mean for a second. You've come across what's called an arithmetic mean. You know what a mean is?
Yeah.
It's in some sense an average. What's the average of 8 and 2?
5.
How'd you get that?
Add together, divided by 2.
Add together, divided by 2. That's the arithmetic mean. Now we're going to talk about a proportional mean. What is a proportional mean? I want you to find me the number such that 4, here's how you would say it. 4 goes to what as that number goes to 9? Find the number x such that 4 goes to x as x goes to 9. What's the number that maintains the proportionality? It's called the mean proportionality, or sometimes called the geometric mean, or the proportional mean. So I'm looking for the number such that 4 goes to x as x goes to 9. You with me? Cross multiply. That times that equals that times that. We get x squared is equal to 36. Or in other words, x is equal to what? 6. So 4 goes to 6 as 6 goes to 9. 4 6 is exactly 2/3. 6 9 is exactly 2/3. 6 was the number we were looking for. It's called a geometric mean. What is the average of 4 and 9? 13 halves, or 6.5. So different from 6. Not the same number. Why is it sometimes called the geometric mean? Let's really quick come back to this picture. So I'm going to call this distance from B to D x, and the distance from D to C y. You with me? And I'm going to call this altitude h. You with me? So then, since all these triangles are similar to each other, this is h right here, this is h right here, that's h and that's h, maybe you can stick in the middle. Those are both h, right?
Yeah.
So then x over h is equal to what, looking at the bottom triangles? X over h is equal to h over y. Or in other words, h squared is equal to x times y. Let's put an h right here instead of a x there, so that you see how they're the same. And so h squared is equal to x times y, or h is equal to the square root of x times y. How could you geometrically solve this problem? The way that you would geometrically solve the problem is you would draw a side of length 4, you would draw another side of length 9. We talk about how you would do this, but then you construct the right triangle whose point at the top would be directly above that point.
Oh, I see.
And then the h here will be your geometric mean. If I constructed it so that that's a right triangle and that's 4 and that's 9, then that will be 6. So your geometric mean and your proportional mean, same thing. Just a definition, another type of mean that shows up in math, just like you're used to taking averages. The proportional mean, and why it's sometimes called the geometric mean. With me so far? Okay, So now with that, I think we're ready to prove the Pythagorean theorem. Let me quickly make sure I didn't skip anything else the author talked about. All right, I think we're good. So let's prove the Pythagorean theorem. Okay, you all know the Pythagorean theorem, so let's reset up our picture here. What is a Pythagorean theorem? If I give you a right triangle, such that one of the lengths has length little a, one of the sides has length little b, and the hypotenuse has length c,
Then a squared plus b squared is.
then a squared plus b squared equals c squared. This is a big C for that point. So I'm trying to show that a squared plus b squared equals c squared. You with me? Now, same triangle, splitting it up down here. That's height h, that's height h. Since these triangles are similar, I know that, let's see, well, let's write the information we know right here. This is little a, and this is little b, right? So now, let me quickly say, looking at how this is similar to this, tell me what x over a is equal to. X over a is equal to what from the big picture? Notice that we're doing small side to the hypotenuse. Small side over the hypotenuse is equal to
A over C.
a over c, small side over the hypotenuse. The smallest side of this triangle divided by the biggest side of this triangle is equal to the smallest side of this triangle divided by the biggest side of that triangle because they're similar triangles. You with me? Now, just doing the algebra from this, multiply both sides by a, and I get x is equal to a squared over c. With me? Going to do a similar thing now looking at this triangle. Let's look at y over b. Y over b, we are looking at the middle side, not the small side, but the middle length side over the longest side, is equal to what?
B over C.
B over c. So the second largest side over the largest side is equal to the second largest side over the largest side because the triangles are similar. You see that? Multiply both sides by b, and that gives me y is equal to what?
B squared over C.
B squared over c. Good. Okay, now, what does c here equal?
X plus y.
X plus y. Which is equal to a squared over c plus b squared over c. So c is equal to a squared over c plus b squared over c. Multiply both sides by c. Multiplying this side by c, I get c squared. Is equal to, when I take this term and I multiply it by c, that cancels out the c top and bottom, I'm left with an a squared. Plus multiply this term by c, cancels out the c top and bottom, I'm left with b squared. Pythagorean theorem. I like the one where we draw out the whole pictures better and show it in terms of the areas. I think that one's more intuitive. But this is a neat way to do it based off of the similarity of the right triangles. You with me?
Yeah.
Now I'm going to prove the converse of the Pythagorean theorem. What's the converse of the Pythagorean theorem? I'm going to prove that if you give me a triangle, you give me some triangle with side lengths A, B, and C, and you do it in such a way that a squared plus b squared equals c squared,
That's right.
then it is in fact a right triangle. So the Pythagorean theorem says that if it's a right triangle, a squared plus b squared equals c squared. Now we're going to do the converse. If you give me a triangle such that a squared plus b squared equals c squared, then the angle opposite the side c is in fact a right angle. That's what we're going to prove.
What about an equilateral triangle? Doesn't that satisfy a squared plus b squared equals c squared? Yeah, like an equilateral triangle with side lengths of 1.
What's 1 squared plus 1 squared?
Oh, it's 2.
Which is not 1 squared.
Gotcha.
Okay. So I'm trying to prove that this triangle is in fact a right triangle. Okay, here's how I'm going to do it. I'm going to come down here. I'm just going to construct a right angle. So there's for sure a right angle. And I'm going to mark off of this side a length the same big as B. I'm going to mark off of this side a length the same big as A.
Okay.
And then make that triangle.
And you're gonna show that side is equal to C.
Well, I know from the Pythagorean theorem that this side is a squared plus b squared under the radical.
Wow, so it's false. Correct.
So I know that this is the square root of a squared plus b squared by the Pythagorean theorem, which is exactly C.
Right.
So using the Pythagorean theorem, I know that this side length is C. Now how does this triangle compare to this triangle?
No, they're the same triangle.
Well, they're congruent. Stronger than similar. They're congruent. How do I know they're congruent?
Because all their sides are the same.
By side, side, side. So this triangle is congruent to that triangle. So then this angle is congruent to that angle.
Right.
Make sense?
Yep. Makes sense.
So we started out with a triangle. We constructed a right triangle that had two sides the same length. And it turns out that the third side was also the same length. And therefore the two triangles were congruent, and so that had to be a right angle. That was all the thinking.
Gotcha.
Follow that? Okay. Our last theorem has to do with semicircles.
Oh, sick.
So see if I can, I'm terrible at drawing circles. See if I can draw just a remotely half-decent semicircle. Not good. You don't need to laugh. Come on. All right. Now, here's what we're going to do. I'm going to pick this point. And then I'm going to pick any other point along the arc. Doesn't matter where. Pick a point, any point, as long as it's on the arc.
You prove it's the right triangle.
So, like that point. I am going to prove that this resulting triangle is a right triangle every time. We'll say that was the center of the circle. Our circle has radius r, so this distance right here from there to there is r. You with me?
Yeah.
Now I'm going to show you the standard way to prove it that we can't use yet because we don't have degrees. But here's the standard way to prove it. We could, red's what I'm ultimately going to need to erase, so. We could draw a point down to there. What is this distance?
R.
R, that's the radius of the circle. So now look at this triangle. What kind of triangle is it? It's an isosceles triangle. And so the base angles are congruent. And so I know that this angle is congruent to this angle. Similarly, this is also R right here, right?
Yeah.
So this triangle right here is a isosceles triangle. And so I know that this angle is congruent to this angle. You with me?
Yeah.
Now, let's see how I want to say this. We'll call this angle right here I'm just going to name all these angles really quick. So, red angle, let's call that angle alpha. Green angle, we'll call that beta. This angle right here, what should we call that one?
Bob.
Call it what?
Bob.
Bob. Well, we already used a beta.
It's called gamma if you want.
We'll use a gamma. And then this one right here we'll call, I'm afraid to use something like pi. Theta. Theta, there we go, good one. We'll do theta and phi. Those are pretty common ones. Okay, so I've named all those four angles. Now, I know that 2 alpha we'll keep going. 2 alpha plus 2 beta plus theta plus phi has to equal what? What's the sum of all the angles in a triangle? A straight angle or 180 degrees. We'll do it in terms of degrees.
Okay.
So the sum of these three is 180, and the sum of these three is 180. Add them together, you get 360.
Right.
You with me?
Yeah.
Now, theta plus phi is
Straight angle.
straight angle or 180. So this is really 180 degrees. Let me just be super explicit. Just showing you the standard way this is shown.
So
Because I know those two together are 180.
2 alpha
subtract 180 from both sides, and I get that 2 alpha plus 2 beta is equal to what? 180. Divide through by 2, and I get alpha plus beta is equal to what? 90. And so alpha plus beta is 90 degrees. Which is a right angle. There's a standard way it's done. Now we can't do it that way because we don't have a notion of degrees yet. We're calling a straight angle 180 degrees. So we're going to have to do it a different way. Just showing you that's the standard way.
Can't like try or mess out without using degrees.
Could you do it without the degrees?
Like with the angle sums, just without degrees.
You can do it with angle sums and coming up with ways of measure. It's like we need to talk about the measurement of the angles without actually having
The measurement of the angles.
defined measurements of the angles yet.
I see.
So,
So we could just talk about straight angles and.
well, we're not going to come at this using angles at all. We're going to come at it using similarity, the relationships we have over there, just letting you know that that is the common way to do it. Okay, so now on this triangle, this time what I'm going to do is I'm going to drop an altitude down from here. With me so far?
Yep.
I may call this distance, whatever it is, x. I may call this distance y. I may call the length of this side of the triangle, little a, whatever that is. The length of this side of the triangle, little b. And then this total length right here, I may call little c. What am I trying to prove? A squared plus b squared equals c squared.
Right.
That's what I'm trying to prove. If a squared plus b squared equals c squared, then we have a right triangle. So that's what remains to be shown.
Okay.
You with me?
Yeah.
Okay. So we're just going to take the bull by the horn, so to speak, and just brute force calculate what's a squared plus b squared.
Okay.
All right. So first off, what is a in terms of x and y here?
It's the square root of x times y.
I know that looking at this triangle, I know that x squared plus y squared equals a squared. You with me?
Yeah.
So I'm trying to figure out what a squared plus b squared is. A squared is equal to, would it be easier to start with c squared and go backwards? I don't know. We'll keep going with this to see if we get stuck and then go to c and work backwards. Not sure how I'm going to do this yet, just figuring it out as we go. Okay, so a squared plus b squared. I know that a squared is the same thing as x squared plus y squared. Is plus, what is, from this triangle, what do I know? What is this side length?
It's c minus x.
It's c minus x. If this total length is c, then this is c minus x. So I know that y squared plus c minus x squared is equal to b squared.
Yeah.
So, here's a squared. B squared is equal to this thing. So plus y squared plus c minus x all squared. Did I do that correctly?
It appears so.
Don't let me make any mistakes. All right, let's square this thing out. So over here we have x squared plus 2y squared. That's just these terms. We have one of those and two of those, right?
Yeah.
Now multiply this out. C times c is
C squared
c squared.
plus b.
We have c times negative x and negative x times c, which is going to be minus 2xc.
Right.
And then we're going to have plus x squared.
I think it cancels out. Oh no, there's 2x squared there. 2x squared plus 2y squared plus c squared minus 2xc.
Yeah. Let's see, I'm going to need to write this in terms of r. Let's think about how to do this. I know that this right here is r. I know that c is the same thing as 2r.
Why do you have to write it in terms of r?
Huh?
Why do you have to write it in terms of r?
I need to somehow relate my x's and my y's together.
I see.
What would be the right way to do that? Always a little dangerous trying to do it on the fly. Am I going to need this triangle as well? Let's see, that would give me r. Yeah, we can't use any trig.
Yeah, just think about that.
Can't use the angles, can't use the trig, so God has stopped my brain from going there.
That's what I was thinking.
Yeah. Let us think about this. X we have in terms of A, but then we also have the Y there. Y, looking at this triangle, I could call this distance. Let me scribble this triangle to the side. Looking at this one, I have an R here, I have a Y here. Down here, this base is going to be R minus X, is how I could think about it. You see that?
Yeah.
And so, I know that this squared plus this squared equals that squared, or in other words, I know that Y is equal to the square root of this squared minus this squared.
Does that cancel out? That should cancel out, right? R squared minus R times, or R minus X squared.
Well, let's see. R squared minus, let's see, R times R gives me R squared. R times negative X gives me minus
Rx, 2Rx.
2Rx, because we have that times that and that times that. Then we have plus X squared, right? And that is going to be equal to R squared minus R squared plus 2Rx minus X squared. The R's go out, and we get 2Rx minus X squared. So we can rewrite Y is equal to the square root of 2Rx minus X squared. Right?
An R there. Do we want to, are we trying to cancel out the R? Or are we good with this?
We need to somehow see that the X's and Y's in this expression cancel each other out.
Okay, dude.
They have to. We have to be left with C squared when it's all said and done.
Right.
So I'm trying to show that A squared plus B squared equals C squared, which means somehow this information needs to somehow secretly cancel out.
So
So
we're
let's
gonna substitute.
just keep messing with it. So I have 2x squared plus 2y squared minus 2xc plus c squared, right?
Would you use theorem 911 at all?
Which one is that one?
That's,
That is Pythagorean here.
no, that's one right before it.
Oh, where?
Where
Well-
x over a is equal to a over c.
Let's just quickly use the fact that
Surely x to y.
Your geometry.
x goes to y. We probably could have done something like that. All right, let's keep thinking with this for a second. What does y squared equal then? Y squared is equal to 2rx minus x squared, right?
Yeah.
So there's our y squared. So we have 2x squared plus 2y squared. So that's going to be 4rx
Minus X squared.
minus 2x squared. Remember, we're multiplying it by 2.
Right.
That times 2 and that times 2. So x squared plus 2y squared minus 2xc plus
C squared.
c squared.
So the
All right,
2x
so this cancels with this.
Sweet.
You see that?
So we have 4Rx minus 2xc.
And what is c in terms of r?
Just 2R.
Just 2r. So this is going to be equal to, we have 4rx, I'm writing this now, 2xc. C is 2r.
You could also rewrite R in terms of C half.
Well, we're good now because 4rx minus 2 times 2 is 4rx plus c squared.
Isn't that
And then we get c squared, which is what we wanted. There could have been 1,000 ways that we did this. I just did a brute force way. There was probably a clever way. But I just flat out figured out what it equaled and then figured out how x and y were related to each other because I knew that they were all going to cancel out in the end and we'd be left with c squared. So I had to figure out how to write y in terms of x, substitute it in, and then all my x's should have canceled out.
Now we know it's a right triangle.
Yeah, so since a squared plus b squared equals c squared, we know it has to be a right triangle from the previous theorem.
How do we know that the right angle is where it meets the semicircle? And not at one of the bases?
Because we know when you have this situation, you know that your right angle is opposite your hypotenuse.
Okay.
Okay?
Alright.
Any other questions?
Can I go grab a jacket?
You sure can. Any other questions on the lecture? That's it for today's lecture then. So
Did you do theorem?
just finish the homework. There was one theorem that is a construction type theorem that has to do with talking about two circles close enough to each other intersect for when you do your constructions.
Yeah.
We skipped that one. That's one of those theorems that it's a ton of algebra and almost no payoff. I don't even think the author bothers proving it because it's a mess.
No, they do. They have a proof right there.
There might be a wordy explanation. I don't know. So that's the only theorem in the chapter that we skipped.
Okay, so do we need to use that one?
You don't have to do the construction process.
Oh, sweet, that's right.
But either way, I'm fine with you assuming that those two circles intersect. It's one of the things even Euclid assumed.
So
So
wait, construction problems as in if they ever ask us to like,
if it says construct this or that, you don't have to do the construction.
oh.
Okay.
How do I process that?
Any other questions? All right, then that's it for this chapter. Done with similar triangles.